well, yeah, I think this is correct, so we'll get started then. Okay. So in Chapter 7, or last week, we did a little bit of Chapter 7 and a little bit of Chapter 8. We looked at t-tests for independent samples. And we also looked at t-tests for paired data. Okay. Now let me look back through our lecture slides for, I think, where are we? Spring XL13. One of these, I think in one of the slides I showed kind of a map of where we're headed. So I want, here we are. Okay, no, that's not it. I don't know where it went. Oh, no, here it is. Okay. So I said, now we are in the land of statistical inference, and we can look at things with a numeric response and a categorical predictor, and that's how we ended up with t-tests. Okay. And we looked at both t-tests for independent samples and for paired data. Okay, so if you have a numeric response, categorical predictor. Categorical predictor in this case for t-tests would be you have one sample that is, men, and another sample that's women. Okay, so you have two categories there, in that case men and women, and you're comparing something like their height. So you have a numeric response, height, categorical predictor, which sex they are, okay? Or, whatever other numeric response, and you are dividing them into two groups, okay? And we said you can do it for independent groups, and we also did them for paired data, okay? There's actually one more test that comes in here, same thing, numeric response, categorical predictor, two groups, and we're going to learn a non-parametric test called the Wilcox and Mann-Whitney test. Okay, so I'll write that up there. Okay, so that's going to be the first part of today's lesson, is numeric response, categorical predictor, but then not a t-test, but something else. Okay, and then the rest of today, we're going to do categorical responses with no predictor and categorical responses with categorical predictors. Okay, so we're doing a bunch of different stuff, and I don't want it to get all jumbled in your head. So today we're going to do one more categorical predictor, numeric response, and then the rest will be categorical response with either no predictor or categorical predictor. Okay. And then next week we'll cover ANOVA, and then the week after that we'll cover regression. Okay, so this is kind of how it all fits together. Okay, so we're learning different statistical methods depending on the type of data we are encountering or experiencing. Is that okay? All right. So today we will learn the Wilcoxon Mann-Whitney test. These are three people's last names, and they all kind of get credit for this test. this is essentially the same as the Wilcoxon rank sum test. Or sometimes this is also called the Mann-Whitney U test. So there's, they come up with several different names, okay? Now, I will say the Wilcoxon rank sum test is different from the Wilcox and Mann-Whitney test. However, the underlying results and the underlying mathematics turned out to be the same. They just didn't realize it at the time, okay? And so if you pick up a different textbook, they might talk about the Wilcoxon rank sum test, okay? And actually in R, they've implemented the Wilcoxon rank sum test, okay? But essentially, if you want to do a Wilcox and Mann-Whitney test, you can run the Wilcoxon rank sum test instead, and it's fine, okay? But our textbook covers Wilcox and Mann-Whitney, so that's what we're going to cover. Okay, so when do we use this? Okay, so we use it pretty much under the same conditions as the t-test for independent samples, with one important distinction, okay? We use this test, in situations similar to a t-test with independent samples. Okay, and so here, those conditions are, you've got a numeric response, okay, you have two independent samples, okay, each representing a different population. Okay, so that's very similar to a t-test for independent samples. The key here, the important distinction, is that for using the t-test, there is an underlying assumption that we can apply the central limit theorem. Okay, distinction. So to use the t-test, we assume that the central limit theorem can be applied to the sampling distribution of y bar. Okay. That sounds familiar to you guys, at least? Okay. And for the Wilcoxon rank sum test, or the Wilcox and Mann-Whitney test, so I'm going to just abbreviate WMW test, okay, we make no such assumptions about, so this is where the speakers go crazy loud. Okay, we make no assumptions like that. Okay. So, in fact, this, so in the t-test, we have hypotheses, and the hypotheses are about the population parameter mu. Okay? So let me just further distinctions. Okay? With the t-test, our hypotheses are about mu. Okay? let me write, are about population parameter mu, or parameters, population parameters mu, maybe mu1 and mu2, mu1 and mu2. Second. Okay, and in the Wilcox and Mann-Whitney test, we don't even use the word parameters. Okay, the Wilcox and Mann-Whitney test does not use the word parameters, or does not use parameters. Okay, so we don't make statements about the mean of the population. Okay, and so the Wilcoxon, the Wilcoxon-Mann-Whitney test falls under a category of statistical methods called nonparametric statistics. Okay, So nonparametric statistics is this whole branch of statistics that you could spend, you know, your life researching and investigating methods for nonparametric statistics, and a good amount of work has been developed. We're going to spend maybe 30-40 minutes on it today, and that will be your entire exposure to nonparametric statistics. But I want you to know that there is a lot of stuff out there, okay? And so, you know, when do we use nonparametric statistics? So, if you don't want to make assumptions about the underlying data, that would be when it might make sense to use nonparametric statistics, okay? So let me just... So use nonparametric statistics when you do not want to make any assumptions about underlying data. Okay, this is in opposition or in contrast to the t-test, where we are assuming the sampling distribution of y bar follows the normal distribution, right? When we apply the central limit theorem, we're saying y bar comes from a normal distribution. Okay, so in contrast to t-test that uses CL central limit theorem and assumes y bar okay. And so the thing is that the central limit theorem applies in many situations. Okay, do you remember the conditions for which the central limit theorem applies? Yeah, when n is large. That's probably the biggest, the one that is most readily violated. Okay, we say the samples are drawn from randomly, and if you've got two samples for the t-test, you've got independent samples. So random and independent. That your population is big, or that your sample is not too large, and then that your sample is not too small. So as long as n is large, you can use the central limit theorem. But sometimes you have a small n, and your underlying data is not symmetric. Okay, And in that case, that's a prime opportunity to use Wilcox and Mann-Whitney. So most common scenario, to use Wilcoxon, Mann-Whitney. Is smaller data set. Okay, so generally less than 25. Smaller data set, and then probably some significant outliers. To indicate that the underlying population is not normally distributed. Okay? So again, just going back to this slide here, we still have numeric response, categorical predictor, and we've got two groups. So we you can have independent t-test and paired t-test, and then there's one more in the Wilcox and Mann-Whitney, and we use that for independent groups, but the underlying data does not seem normal. Okay, so this is probably our most common scenario for Wilcox and Mann-Whitney. Again, assume the data come from independent. The two samples are independent. That's a requirement. Okay, so you know, well, maybe we just want to say, well, I don't generally want to make any assumptions about the underlying data. Why don't I use the Wilcox and Mann-Whitney test all the time? Okay. Well, in general, non-parametric tests are less powerful than their parametric counterparts. Okay. So the Wilcox and Mann-Whitney test pretty much serves the same function as a t-test for independent samples. Okay, you use them in both the same scenarios, except that with the Wilcox and Mann-Whitney test, you're not putting any assumptions on the underlying data. But in general, non-parametric tests are less powerful than their parametric counterparts. So what does it mean to be less powerful? So do you remember the definition of power? Power is equal to 1 minus beta. Beta is the probability of a type 2 error. So to have great power and great responsibility. No, to have great power, what does that mean when it comes to a statistical test?
It's very predictive.
Yeah, it means that when the null hypothesis is false, the test will identify it as such. Okay? When we say the non-parametric test is less powerful, it means it's not going to be as so good at identifying when the null hypothesis is false. Okay, you're more likely to make type 2 errors with a nonparametric test. Okay, so more likely to make type 2 errors. Okay, your data basically need to be more extreme for you to come to a conclusion to reject the null hypothesis. Okay, and if we think about it, that kind of makes sense, right? Because if you make strong assumptions about things, then it often leads you to certain conclusions, and that's where you make mistakes, right? You say, if you assume too much, maybe you made a mistake. And so a lot of times you want to say, well, I don't want to make a decision because I don't want to make any assumptions, okay? And so if you don't make any assumptions about anything, a lot of times you're in these situations where you just don't make any decisions because you don't want to assume too much. And that's kind of similar to nonparametric statistics. You're making a lot fewer assumptions, so you're going to make fewer decisions about rejecting the null hypothesis. And maybe that's what you want because you want to play it safe and you don't want to make any assumptions about the data and make a mistake because you assumed things about the data. But that might not be a good thing either. Okay. And again, we're just learning this one nonparametric test. There's a whole world of nonparametric tests. Pretty much any parametric test we learn, there's going to be a nonparametric counterpart. Okay, there's a nonparametric counterparts to paired tests and things like that, and all of this stuff. It works when you have really skewed data. It's probably a good time to use it. Okay. All right. So let's talk about carrying out the actual Wilcox and Mann-Whitney test, the steps for it. Okay. So Wilcox and Mann-Whitney test. Okay. The hypotheses that you write, you still have a null and an alternative hypothesis, but there's no symbols in the hypothesis because there's no parameters. Okay? So you have to say something along the lines of the null hypothesis is that the distribution of population 1 is the same as the distribution of population 2. Okay, and your alternative, you can have non-directional and directional alternatives. Okay, so non-directional would basically be one of the distributions, or one of the populations, produce, or I should say tends to produce values that are larger than the other population. Okay, so that's non-directional because you're not specifying which population. In a directional one,
could you also write smaller then?
Yeah, smaller, it doesn't matter, okay? And a directional would be population 1, or you specify which population. Population 1 tends to produce values that are larger, or if you want the other direction, smaller than population 2. So now you are stating which population you are expecting to produce larger values. So that would be a directional alternative. Okay? So no symbols for no symbols in the symbols in the hypotheses of non-parametric tests. I don't know what's causing that, the speakers to suddenly get crazy loud.
Is your battery?
Yeah, I switched out my battery yesterday, and it was still doing the same thing. So I don't know. Because I think it's still working now, or is it like completely cut out? No, blah blah blah. Okay. Well, I'll during the break I'll call the help desk. Okay, so once you've established your hypotheses, let's here, I'll try changing the batteries again. Give me a second here. I mean, I guess my unit could be messed up also. Okay. Hello? Testing? Maybe. Oh, well, there it is. Pretty loud. Okay. Let's let me pull up the data here. Okay, so let me just take the data here. Okay, so the idea behind, I'm out, right? It's not working? Okay, so in this data set, we went to the forest and we are looking at soil respiration data. Okay, so I'm not exactly sure what soil respiration is or what it indicates, but we put something in the soil and we measured how much carbon dioxide it gave off in a certain amount of time, okay? And we want to know, is the amount of carbon dioxide it gives off different, or is it carbon dioxide that it absorbs? I don't know. Something about carbon dioxide. Is it different for a section in the area where there was heavy growth and a section in the forest where there was kind of a gap in the growth? So kind of like this dead zone area. Okay, so we looked at two areas in the forest, and we want to know, is there a difference between the soil respiration numbers from the two regions? Okay, and so our null hypothesis is going to be there's no difference in the difference between the populations, and then the alternative is going to be that the population for the growth data tends to produce values larger than the population for the gap data.
Are you just saying that based on what you see?
I think somewhere in the book it was
Okay.
expecting it to be larger. Yeah. Oh, well, I guess they gave you both the non-directional and the directional alternative. Okay. Okay, so step one, which has already been done for you, is put each group's data in order from least to greatest. Okay. And then step two is count how many values in the other column are smaller than the current value. Okay, and ties are worth 0.5. So I will demonstrate. Okay. Did we manage to copy these numbers down? No? Yes? No? Okay. I'll give you guys a moment to do that. Are we good? Alright, so I'm going to look at this number 17, and I'm going to say how many numbers over here are smaller than 17. So 6, 13, 14, 15, and 16. I have 1, 2, 3, 4, 5 numbers that are smaller than 17. I go to 20 and I ask how many numbers over here are smaller than 20. That's okay. So I have 1, 2, 3, 4, 5. 6 numbers in the other column are smaller than 20. Same thing for 22, okay? And so I have 6 numbers over here that are smaller, and then I have a tie, 22, and so that goes down as 6.5, okay? Now if I had another 22 in here, okay, then each tie would count as 0.5, and so I would have 6 and then 6.5 and then 7. So I would write down 7 over here if I had 2 ties in there. Okay, 64, all numbers 1, 2, 3, 4, 5, 6, 7, 8 are smaller. And so for all the values larger than 64, I still have 8 numbers smaller. Okay. And for the gap data, we do the same thing. 6, how many numbers in the other column are smaller than 6? None. 0. 0 numbers are smaller than 13. 0 smaller than 14. 0 smaller than 15, 0 smaller than 16. And at 18 I get 1. At 22 I have 2 numbers that are smaller plus a tie, so I get 2.5. And at 29 I have 3 numbers that are smaller. And that's it. Okay? And then we add each column up. So over here I get a total of 6.5. And then over here I have to do a little bit of math here. 32 plus 12, 44, 49.5. Okay, so you have 2 sums, and whichever one is bigger is your Wilcoxon Mann-Whitney U statistic. This is your test statistic U. I don't know why they use a U, but they do. Okay, so your test statistic, step 3, is sum those values, and the larger is your test statistic. And so we can see that the test statistic, this 49.5, only depends on basically the ranking. Okay? If this is bigger than all of these numbers, it gets 8 points. And it doesn't care that this says 170, this one's 64, and this one's 315. Okay? It just cares that 64 is bigger than the biggest number over here. 315 is the biggest number over here. Okay? So all of these numbers contribute 8 points towards the test statistic. Okay? And you could imagine for something like the t-test, it would contribute a lot more, right? Being changing your overall mean, okay? Because the mean is affected by outliers and things like that. These, it doesn't care that these are outliers or huge. They're all contributing the same. Okay, so that's kind of where you see the non-parametric part. Okay, and so at this point we just look up 49.5 in a reference table. Okay, and so the Wilcox and Mann-Whitney test has its own reference table, and we look this up. Okay, so step 4, look up U in the reference table. Okay, so to use the reference table, let's pull that up. That's the wrong reference table. So this is table 6. Okay, you see there's 2 columns. You have an n and an n prime. Okay, so basically you just count how many values do you have. What's the n over here? We have 1, 2, 3, 4, 5, 6, 7. So n over here is 7, and n over here is 8. Okay, so whichever one is bigger is n, and whichever one is smaller is n prime. So in our case, we have an 8 and a 7, so n is going to be 8, and n prime is going to be 7. Oops. Is that okay? So you got 2 n's. Whichever is the bigger n is your n. Whichever is the smaller n becomes n prime. I know. And then so we look up n is equal to 8. Then I go to the row n prime equal to 7. And then we're going to look up the test statistic 49.5. Okay. So here I get at 48, if my test statistic was 48, my tail area is 0.021. If my test statistic was 50, my tail area is 0.0093. Can you guys see that in your reference table, kind of? Huh? Where am I looking?
Can you show it one more time?
Yeah. Okay, so I'm going to look up, so from here I have n is 8 and n prime is 7, right? That's okay. So I'm going to go to the row n8, and then within the 8s I go 2, 3, 4, 5, 6, 7, and this is going to be the row that I'm using. So let me just, so this row. Is that okay?
Yeah, I get it.
Okay, and then so looking at this row, I'm going to look up my test statistic, which is 49.5. Okay, so if I didn't have this tie, I would probably end up with 50 or 49 or something. Okay, so if I had 50 exactly, then the area in my tails would be 0.0093. Okay. But again, I'm getting, I'm in one of those situations where my exact test statistic isn't listed, so I have to say my tail area is between 0.0093 and 0.021. Yeah, I know. Okay, so my tail area is between, what did I say? 0.021 and 0.0093. 0.021 and 0.0093. Okay? And if I had a non-directional alternative, this would be my p-value, okay? But if you read, you have to read the top of the table, and all of these tables kind of kill me in this because they're not consistent. But at least they tell you. At least they're consistent in their warnings, I guess. So right here it says, look up your statistic U in bold type, and the corresponding p-values for a non-directional alternative is in italics. Directional p-values are found by dividing the numbers in italics in half. Is that okay? So my alternative is indeed directional, saying growth data tend to be larger than gap data. So my p-value would then be half of my tail area. So in this case I would do 0.021 divided by 2, and I would get 0.0105, and I divide 0.0093 by 2, and I get 0.00465, and so my p-value is between these two numbers. And that's my final answer, regarding my p-value at least.
So the table that we have goes to 10. And you said we could use the t-test, once we got about 30.
Yeah.
So what happens?
Okay, so your book actually has more. Okay, so the bottom of this thing says continued. There are more in your textbook, or actually not the second edition or whatever, 5th edition textbook, because they got cheap on the tables they include.
Well, I'm not worried about
yeah.
it. It's just
Yeah, so they do have more more things, and probably, to be honest, you would use the computer.
Yeah, well, right. That's what I figured. I guess I was just making.
Yeah, and no one's asking me, hey, where did all of these numbers come from, which is a complicated answer. And actually, I don't know how they calculated it mathematically. I know how you could get these numbers through simulations, but I don't know how to actually I don't know the math behind it. So don't ask me to prove the math. But I could show you the simulation, which is not that exciting either. But it comes from, you shuffle all of these numbers around. I guess they must have just in every permutation of a shuffle, and you see how often you get these weird rankings. And so this is a nonparametric test, okay? You're not doing no calculating of means, no calculating of standard deviations. You're just kind of comparing ranks, which one is bigger and which one is smaller, and that's how it goes, okay? So if we said, however, you still get a p-value, okay? And so if I said use alpha equal to 5%, what would our conclusion be? So my p-value is between 0.00465 and 0.0105. So I would reject, right? So if my, so let me just copy this. So if my p-value is, if my alpha is 5%, my p-value is definitely less than 5%. And so we would reject the null hypothesis, and that means, okay, so if alpha equals 0.05, we reject the null hypothesis, and we would say our data provides evidence against the null hypothesis, and it supports the idea that the population for the growth data tends to produce values larger than the population for the gap data. Okay, so our data supports the alternative. We have evidence that the population for growth data tends to produce values larger than the population for gap data. Okay. Is that okay? All right, let's take a little pause here